Okay, so for this deep dive, we've got something a little different. Our source is a product listing.
Yeah, but it's so dense it reads like a spec sheet for a spaceship part.
It really does.
Yeah.
We're looking at the NTI E-RTDS-A1112. It's an all-purpose RTD sensor.
And that's our mission, right? To figure out what all-purpose actually means when it comes to industrial precision.
Exactly. And the first thing that just grabs you is the temperature span the suit
Right.
can supposedly handle.
It's just wild, isn't it?
I mean, we're talking about an application range from minus 328 degrees Fahrenheit
Which is incredibly cold.
all the way up to 1112 degrees Fahrenheit. That's a huge window for just one device.
And to handle that, you need some serious durability. I mean, the construction has to be top-notch.
Which it looks like it is. It's a 6-inch probe made of 316 stainless steel.
And that 316 grade is important. It's not just any steel. It's built for corrosive environments, with salts or chlorides. That's part of its all-purpose claim.
Okay, but I saw something interesting about the wiring. The probe can take the heat, but the 40-inch lead cable is only rated up to 482 degrees Fahrenheit. So why the huge difference?
That's a great catch. It's a classic engineering trade-off. The sensor tip, the part doing the work, is in the extreme environment.
Right.
But the cable and all the electronics it connects to are, well, they're assumed to be a safe distance away. High-temp insulation for wiring gets very expensive, very fast.
So it's a cost and design compromise. Okay, that makes sense. Let's get into the core of how it works. The technical signature, 100 ohm peak, 385.
Right. This is the sensor's whole identity. It's a resistance temperature detector.
So the P is platinum. What about the other numbers?
The 100 ohm is its resistance at exactly 0 degrees Celsius. It's the baseline. And the 385, that's the temperature coefficient.
The what?
It's basically the standardized curve that defines how much the resistance changes as the temperature goes up. It's the industry handshake. Every controller is programmed to understand that exact curve.
Okay, so here's where I think we find the real nugget. This difference between its total range and its accuracy range.
Exactly. The manufacturer says it can be used across that massive window we talked about.
But they only guarantee the really high accuracy. We're talking plus or minus 0.27 degrees Fahrenheit in a much smaller zone.
A much smaller zone, from minus 148 up to 842 degrees Fahrenheit.
So that's its sweet spot.
That's where it's rock solid reliable. Outside of that, it still works. But maintaining that perfect linear accuracy gets, well, much harder.
So it's a universal tool, but for surgical precision, you have to stay within that core range.
Precisely.
And this sensor, it doesn't just spit out a temperature reading, does it? It needs some help.
Oh, absolutely not. It just outputs a changing resistance. It needs friends. It requires an external transmitter, like the ES420MA24V mentioned in the source.
And what does that do?
It converts that resistance signal into a standard 4 to 20 milliamp current loop. That's the universal language for industrial controls, for the SCADA systems like the E2D or 5D.
And those transmitters have their own temperature windows they're designed for.
They do. You have ones for tighter ranges, like for HVAC, and then you have the big one.
The E-RTDT-1562.
That's the one, the true partner for the sensor. It's built for that huge, expansive range.
So to sum it all up, for about $270, you get this incredibly tough stainless steel sensor that has certified precision over a really useful range.
You're buying versatility? But the most interesting detail for me is that design asymmetry we found.
Look at the transmitter.
Yeah. That E-RTDT-1562 transmitter can handle temperatures all the way up to 1,562 degrees Fahrenheit.
Which is way hotter than the sensor's own limit of 1112.
450 degrees hotter.
So that really leaves you with a final question to think about, doesn't it? If the monitoring system is ready to read up to 1,562 degrees, but the sensor itself taps out at 1112, what's the true limiting factor here? Is it the steel starting to fatigue over the long term? Is it the sheer cost of the platinum you'd need to keep the accuracy curve stable at those temperatures? Or is it something else entirely? It really makes you think about where the real edge of all-purpose is.